For decades, humanity has relied on space telescopes like Hubble and James Webb to reveal the hidden universe. But something different is happening now. A giant observatory on Earth has begun watching the sky on a scale that could completely change astronomy. The Vera C. Rubin Observatory is designed to do something most telescopes were never built to do. Instead of staring at one galaxy, one nebula, or one star system for a long time, Rubin surveys enormous portions of the sky again and again. Its massive camera contains about 3.2 billion pixels, allowing it to capture huge areas of the universe in remarkable detail. And that means astronomers are no longer limited to asking what exists in space. They can also ask what is changing. That difference is enormous. Imagine looking at the night sky tonight and taking a photograph. You would see thousands of stars. Now imagine taking the same photograph again a few nights later and comparing every detail. One star has suddenly become brighter. A tiny object has moved. A distant explosion has appeared. A faint galaxy has changed. A new streak crosses the image. Rubin is designed to find those changes. Its location in Chile gives it exceptionally dark and dry skies, creating ideal conditions for a major ground-based survey. Combined with its enormous camera and wide field of view, the observatory can capture sections of the sky far larger than those typically observed by space telescopes. Instead of seeing one small cosmic window, Rubin can step back and examine the larger landscape. That became obvious in its early observations. The first major images revealed huge collections of stars, galaxies, clusters, and glowing clouds of gas. Thousands of distant galaxies appear in a single enormous scene. Some are spiral galaxies. Others are interacting with neighboring galaxies. And many are so faint that they become visible only when the image is enlarged. What makes these images remarkable is not simply their beauty. It is their scale. A telescope like Hubble can provide extraordinary close-up views of individual objects. Rubin is built for something different. It shows the surroundings. A nebula is no longer just a glowing cloud. It becomes part of a much larger region containing stars, clusters, dust, and distant galaxies. That broader perspective could help scientists understand how individual objects fit into the enormous structure of the universe. But Rubin's mission goes far beyond taking impressive photographs. One of its most important goals is the search for clues about dark matter and dark energy. Dark matter cannot be seen directly, yet its gravity influences the movement and distribution of galaxies. Dark energy is associated with the accelerating expansion of the universe. Both remain among the biggest mysteries in modern science. By surveying enormous numbers of galaxies, Rubin can help scientists search for patterns and gravitational effects that may reveal more about these invisible forces. The observatory will also become a powerful asteroid hunter. During early observations, Rubin detected thousands of previously unknown moving objects. Among them were near-Earth asteroids. That matters because finding an asteroid is only the first step. Scientists need multiple observations to determine its orbit and predict where it will travel. The earlier a potentially dangerous object is discovered, the more time researchers have to understand its trajectory. And Rubin's repeated scans could dramatically improve that process. But asteroids are only part of the story. Astronomers are also searching for something even more unusual. Objects that came from outside our solar system. Only a small number of interstellar visitors have been confirmed so far, and they were discovered almost by chance. They move quickly, they can be extremely faint, and they may remain visible for only a short period. Rubin's enormous field of view could give scientists a much better chance of finding future visitors. That would be scientifically extraordinary. An interstellar object is essentially a piece of another planetary system passing through ours. Its chemical composition could reveal how planets form around other stars. Its motion could provide clues about its origin. And with enough discoveries, astronomers could begin comparing material from completely different planetary systems. Rubin is also designed to catch cosmic explosions and other temporary events. A star can suddenly explode. A previously quiet source can dramatically brighten. A black hole can tear apart a nearby star. A faint object can appear for only a few days before disappearing again. These events can easily be missed by traditional observing programs. Rubin approaches the problem differently. It repeatedly surveys the same regions and compares new observations with old ones. That makes the telescope more like a cosmic surveillance system. It watches for change. And whenever something unusual happens, astronomers can be alerted and use other telescopes to study the event in greater detail. This could transform astronomy. Rubin may discover an event that another telescope then investigates with extreme precision. In that way, ground-based and space-based observatories become partners. Rubin finds the mystery. Other telescopes investigate it. There is another major mystery Rubin can help solve much closer to home. The structure of the Milky Way. Our galaxy contains enormous numbers of stars, but mapping its outer regions is difficult. Some of the faintest and oldest stars are scattered through the galactic halo, far from the bright center. Among them are RR Lyrae stars, which change brightness in predictable ways. Because their behavior allows astronomers to estimate distance, they can act like markers scattered through the galaxy. By finding many of these stars, Rubin can help reconstruct the three-dimensional structure of the Milky Way. It could reveal ancient streams of stars left behind by destroyed galaxies. It could uncover hidden dwarf galaxies. And it could provide a clearer picture of how our galaxy grew over billions of years. But all of this creates another massive challenge. Data. Rubin is expected to generate an enormous amount of information throughout its survey. Every image contains millions of measurements. Every night adds more. And every new observation must be processed, compared, categorized, and stored. This means Rubin isn't simply building a collection of photographs. It is creating a constantly changing digital map of the universe. A map where objects can be tracked over time. A map where changes become discoveries. And a map that continues to expand with every new observation. That could also bring astronomy closer to the public. Huge interactive datasets can allow students, researchers, and astronomy enthusiasts to explore the same cosmic landscapes that scientists are studying. A person could zoom through a massive field of galaxies, move toward a star cluster, inspect a faint object, and possibly notice something unusual. In the future, some discoveries may begin with a scientist. Others may begin with someone simply looking at the data.